Okay, welcome you all to the next numerical practice problem on transformer session by Dr. S.J.Sarkar in basic electrical engineering classes. Now, this is the second problem what we would be discussing here. This is related to the open circuit and short circuit test of a transformer. So, from that actually we have to find out some quantities. So let's see the problem. So what is given? A given transformer is 5 kVA transformer, 100 by 200 volt, 50 Hz single phase transformer, and we had performed the open circuit and short circuit test on it, and the readings are given here. So from that we have to find out the core parameter and winding parameter. So we know when we would be performing this winding short circuit test, we will be finding out the winding parameter, but that winding parameter will be actually towards the side where we will be performing the short circuit test. It's not that we will be finding out R1, R2, X1, X2 individually, but we will be getting some R equivalent and X equivalent. Or in another way, we could say that we will be getting the resistance or reactance referred to the side where we will be performing the short circuit test. So generally, what is being done is that we will be performing the short circuit test in the high voltage side. So whatever winding parameter means RHP is the resistance referred to high voltage side, and reactance referred to high voltage side would be getting that. So let's see what exactly we are trying to find it out. So what is given there? We know that the rating of the transformer is 5 kVA, so it is 5000 VA. High voltage side voltage is 200 volt. Low voltage side voltage is 100 volt. This is given, and frequency is given 50 Hz. Okay, by the way, after finding out this core and winding parameter, we also have to find out what is the total loss occurring in the transformer during half load and full load. And therefore, finally we have to find out what will be the efficiency of the transformer at full load while operating at 0.8 power factor lagging. So we'll be finding out what is the total losses. Now once losses are known, so for a given power factor, what is the output of the transformer we are going to compute. Now from the output and output plus losses, we are going to get the efficiency. So that is what the basic ideology of this particular problem. So these are the data what are given to you. So from the data, what about the current in the low voltage side? The rated current in the low voltage side will be S by VLV, because it's what kVA means V into I. So basically this ILV, when we are going to put all the value that we are going to get, it is 50 ampere, and IHV, that would be again S by VHV, that we are going to get 25 ampere. So these are basically what? These are the rated current in LV and HV windings. Why we are going to find out this, it would be clear when we will be going in the details of the problem. So these are the data which are available. Now let us start with the first thing, that is the open circuit test. So we will be performing the open circuit test. Why would we be performing the open circuit test? So in case of a transformer, generally what is being done, that we will be performing this open circuit test in the low voltage side with high voltage open. This is what is actually done in case of a open circuit test. So what is given? In the low voltage side, we would be applying the rated voltage. So what is the rated voltage in the low voltage side? It should be 100 volt. It's given. LV is the 100 volt. So again you could see we are applying 100 volt, should be drawing 4 ampere of current. Now what about this current? This should be the no load current. And there would have some power loss occurring in the transformer, so that would be 80. So let us note it down. So the no load would be applying the supply voltage. So later we are calling it VLV only. Rated voltage we are applying. Then it would be drawing some current. So it is open circuit, so the transformer is operating under the no load condition. So the no load current is given, that is 4 ampere. And there is some power loss during open circuit, that is given 80 watt. Now what about this power loss? This power loss in the open circuit is actually due to the losses occurring in the core only, because of much lower current. You could see the rated current is 50 ampere, 25 ampere, that is the rated current is in the high voltage and low voltage side. So you could see in the low voltage side where the rated current is 5 ampere, now only 4 ampere is flowing. So there would have a negligible copper loss. So whatever losses are occurring here, that would be approximately equal to the core loss occurring in the transformer. So this is the core loss that is occurring in the transformer. Now, we know V into I. So can we write the core loss, that would be equal to VLB I naught cos phi naught, where phi naught is basically the angle between the voltage and this no load current. So from that we know all the values, we are putting the things together, so it become P core by VLV I naught. So if we are going to put the value and simplify it, we would be getting the value of cos phi naught, that would be equal to 0.2. So once we are getting the value of cos phi naught, from that what we could do, we can find out sin phi naught, that is root over 1 minus cos square phi naught. So from that, if we are going to compute that sin phi naught, we would be getting 0.98. So this is what we can actually find out from this open circuit test. Now we know cos phi naught, we know sin phi naught. Now understand one point. What is being said? Now I am referring to the phasor diagram of the transformer for the illustration. This is what is actually happening. This is what minus E1, that approximately we had considered it to be approximately equal to V1 here, and there is some flux phi here, there is some magnetizing current Im here, there is some loss component of current IE here, and the vector addition of the two is basically I naught, and this is the angle which we are calling it to be phi naught. This angle is the phi naught. So if that portion is actually considered, so what we could write, can we write this thing here, Im, that is nothing but I naught sin phi naught, and IE, that would be I naught cos phi naught. We can write that one. So from that what we would be doing, we would be finding out what is the magnetizing current and what is the loss component of the current from this data. So we would be finding out Im, that will be equal to I naught sin phi naught. Putting the values, we are going to get, that would be equal to 3.92 ampere, and IE will be I naught cos phi naught. So that would become 0.8 ampere. So we had found up to this point. Now try to understand the thing again. In the equivalent circuit of a transformer, now what is happening? I am only taking the core quantity right now. I am ignoring others. This is R naught, this is JXM, this is I naught, IM, IE, and this voltage will be equal to the applied voltage. Here it would be equal to VLV. This is what is actually going to become. If you could draw the equivalent circuit of a transformer, this is what is going to happen. So can we say that R naught will be equal to VLV divided by IE? This voltage will be VLV by the current IE will be equal to R naught. So solving that, we will be getting R naught equal to 125 ohm. And what about XM? This reactance, that would be VLB by this IM. So it would be VLV divided by IM, and that is coming to be equal to 25.51. So we had found what? We had found the core parameters. So these are what? These are basically this R naught and XM. These are basically what? They are the core parameters what we had found. From how, where we are finding out this core parameter? From this open circuit test we are finding out this core parameter. Now coming to the next thing, that is the short circuit test. So what is happening in case of a short circuit test? The entire short circuit test is done in the LV side with, the entire short circuit test is done in the LV side with short circuited LV. So this is what is happening in case of a short circuit test. Now, what should be happening there? We should apply the rated current through the while performing the short circuit test. Now what is the rated current in the high voltage side? You could see the rated current should be 25 ampere should be the rated current. Now what is the reading what we are having here? We are taking the reading at 20 ampere and having this loss. So let us just note it somewhere. VSC, the short circuit voltage, is 15 volt. The short circuit current is 20 ampere and short circuit power is 100 watt. Now by means of this short circuit test, we can find out what? We can find out the copper loss occurring in the transformer under full load condition. Now you could see we are not applying the full load. So for this current, power is this one. So what will be the full load copper loss? So how to calculate that? See what is happening there. IHV rated is equal to what? 25 ampere. So the full load, or rather I could write it in this way, copper loss at full load will be nothing but, that will be 100 into 25 square by 20 square. If you are going to solve it out, that should be coming to be 156.25 watt. 156.25 watt. So you may ask why it is so. So just understand the analogy. What is power? Power is basically I square into R. So when I is 20, power was 100. So let us suppose P1 that become I1 and P2 that become I2 square into R, because R remain constant. So what we can write, P1 by P2 should be equal to I1 square by I2 square, simply because R will get cancelled out. So from that what we could write, we know P1, from that we could write P2, that would be equal to I2 square by I1 square into P1. So I2 is 25, I1 is 20 and P1 is 100. So we are getting this relationship. So we are getting the full load copper loss by performing this calculation. So this is what is the full load copper loss that is being computed. Now we will be finding out the winding parameter. Now for that purpose, this reading is okay, we can take that thing. Now what about the impedance? ZHP, impedance referred to high voltage side, that would be nothing but VSC by ISC. So VSC by ISC, put the thing, so this should be coming to be 0.75. This is the impedance referred to high voltage side and resistance referred to high voltage side. So can we write it in this way? PSC by ISC square. Power is I square into R, we had already said. So from that simply we are finding out the resistance referred to high voltage side. So from that value is coming to be 0.25 ohm. Now we know ZHV, we know RHV. From that we can compute what? XHV. So XHV would be nothing but root over ZHV square minus RHV square. So from that we would be computing it to be 0.707 ohm. Now what are these value? These are basically the winding parameters referred to HV side. So these are the different parameters what we had found. So this is one part of the problem. So let us go to the next part. We would be using the same data, but we would be doing it in the next part. Just wait a bit. The next portion is we have to find out what are the total losses occurring during the full load and half load and efficiency. So let us come to the transformer losses. Let me start here. A fresh beginning. Transformer losses. So we are focusing on transformer losses. So two cases are there. So in one case, that is what? That is the full load condition. So in full load condition, what is going to happen? In full load condition, we are having two type of losses that are occurring. One is the core loss that would given, that is 80 watt, and what about the copper loss? Cu at full load, we had already computed, that is 156.25 watt. So this is the core loss occurring, this is the copper loss occurring. What is the total loss? That would be P core plus PCU FL, because in a transformer there is no rotating part, so there would not have any loss regarding that. So that equals 236.25 watt. So this is the loss occurring at the full load. Now let us check at the half load. Half load condition. So the core loss is going to remain same because the applied voltage is remaining same. But what is happening to the current? The current is now going to become half. So if the current is going to happen half, so the power loss at half load, can you write it in this way? PCU FL by 4, because current is reduced by half. So from the same relationship what we had done previously, so from that we could say that would be equal to 39.06 watt. So the total power loss would now become, this is total at full load, this is at half load, that would be P core plus PCU HL. So that is coming to be 119.06 watt. So you could see that there is a difference in the power loss occurring in the transformer, different type of load. The core loss remaining the same, but the copper loss changes with the load. So this is one part. Now the next part, we have to find out the efficiency. Efficiency at full load. This is the last portion we have to find out. Now, full load, and what is the condition? It is given at 0.8 pf lag. This is the power factor that is given. So, what we know the efficiency? Efficiency is basically what? The output power by input power. So, we could say it P out by P losses or P total. So here it is in the full load condition, so it should be something like this one. Now, what about into 100? What about P out? The kVA rating of the transformer is given, that is 5000 VA into the power factor. So it becomes 4000 watt will be the power output of the transformer. So how we had found? P out is nothing but S, that is the apparent power, into the power factor. Simply by doing that, we are going to get what is the output power. Okay, so we had found that one. So from that, we will be putting the thing again. It becomes 4000 by 4000. What is the full load? Copper loss 236.25 into 100. So solving it out, it is coming to be 94.42%. So this is what the efficiency of the transformer at full load